I'm going to talk about. There's a lot of stuff that's undone. And the impetus that was given initially led to huge amounts of work. I mean, huge amounts. And you probably need many people to work in the area to fill the void. And that particular time, there were many people who did work in the area and gave inspiration and led to new ideas and stuff. But there are still many things that are not done. And it seems like the algebraic equations are quite easy, so to speak, in inverted commas. However, that's not the case. And of course, having said that, the differential equations or whatever else there is out there, like integral differential equations and difference equations and so on, they become very difficult to handle. And not that they can't. I mean, I think so. Basically, what I'm going to try to talk about here is giving semblance of some ideas, prominent ideas, and if you unravel them, you'll see that they persist even to today. So it's more about differential equation than the algebraic one. But what I'm trying to say here is that the algebraic aspects sits in with the differential equations a lot of times, and some of that is still not even unraveled, even when you speak about it. Okay, so even some of you can do it later on. You can try yourself. Warren's probably interested in this. And I don't know if Joel is. Joel is probably just coming with his fine coat. You can see.
It has to be focused on one.
Yeah, so some motivation. Look, the motivation is quite interesting. The history is very interesting. We talk a lot about the history, like I said earlier on. And ODEs and algebraic invariants, basically linear ones, how they tie to each other. And then you go to the more difficult one of the linear partial differential equations, and that's the content of the honors topic. Some of it is mentioned here, so probably you can list that chapter later on, right? So the different types, hyperbolic, elliptic, parabolic. I'm going to skip through a lot of stuff. I added a few slides compared to what I did in Durban when I did this talk, and everybody wanted the slides, so I don't know if anybody here would want the slides again. So I think we only got 29 minutes. Okay. So, look, coincidentally, the story started at the same time for both algebra and for differential equations. This was, I think David will remember this very clearly when I spoke about this. In 1773, Lagrange is a famous mathematician with no introduction. Consider the invariants of binary quadratic forms, right? Quadratic forms, if you look there. So the squares, there's x, y, there's y squared. So homogeneous, right? So what he noticed was if you do a linear transformation, like let's say with an alpha, a real number, the y doesn't change in that equation, so the x's only change. First of all, for x in terms of x bar plus alpha y, then becomes alpha y bar. Substituting that equation there, this quadratic form maps into exactly the same form. The family is preserved. Its quadratic nature is preserved, you see, except you find in the bar coordinates here, A bar, B bar, C bar. So the coefficients change, right? If you do the calculation itself, this is like a grade 10, grade 11 I should say, exercise, right? If you do this, you find that, so I'm not saying that the grade 11 exercise probably did that, but he saw something more beyond that, right? Okay, so what he saw was that you get the B changes, the B bar, in terms of the alpha, and you got the C bar gets like the quadratic form here, okay? Okay, and So what he noticed in passing was the discriminant. Notice the 2 days for convenience, right? You can leave the 2 out, and if you're going to get a 4 here if you leave the 2 out, right? Okay. If you put the 2 in, usually school books don't put 2's, right? You get this b squared minus a, which is called the discriminant, right? And if you square this b bar squared minus a bar c bar, it remains the same as delta, okay? So in other words, you find that the discriminant remains the same, okay? And not only that, you find that a bar is the same by means of this linear transformation. Yeah, it's linear because you've got x and y. You find that's the case, right? So in passing, Lagrange noted that the discriminant is invariant and a is invariant, okay? Now, if you do the same trick, so what happened here was Lagrange's observation gave to rise of algebra of forms. And algebra of forms meaning that you can do this for cubic forms, quartic forms, n-ary forms. You can generalize, right? And this was vigorously pursued by George Boole in 1841, Cayley 1845, Sylvester, Gordon, and then what remained was like, you get those invariants coming like A and delta, right? Is this the complete set of invariants? If I do a cubic form, quartic form, what is the basis of invariants? What's the complete set of invariants? That's what's the question, right? Hilbert in 1900 proved the basis theorem. Well, he actually mentioned this in the International Congress of Mathematics, but 1890 he proved the basis, the famous theorem on n-ary forms, right? Where you have under transformations, what are the invariants, like delta, A, and so on, okay? However, if you take a simpler example from school days, if you look at the quadratic, again the 2 is for convenience here because we want the delta to be like I said, and you do this transformation x bar is x plus a, and you substitute this into the quadratic equation, it maps into the same family here, right? And you notice this coefficient, which is b bar, this is c bar. So you got a bar, which is a x bar squared, 2b bar x bar plus c bar. And what you find that the discriminant is also invariant here. Okay? Right? And what else you can do here, if I annul this here, right? I can actually solve that equation. So this becomes minus delta over a, and if I put this on the right hand side, it becomes plus delta upon a. If I move the a down, it becomes over a squared. But delta is same as delta bar, a is same as a bar. So notice this equation here is written completely in terms of invariance, right? So you can actually get the quadratic formula out completely by actually doing that. So by just using symmetry or mapping this equation to the same form and working on the invariance. Okay. Now there's another aspect that comes up here. You can look at this from a point of view of what are the so-called patterns of this equation that enables you to map it to the same form, and you call that the equivalence transformation that leaves it equivalent form, right? And from there you can construct these invariants. This is different from completing the square. This is very different from completing the square. The algorithmic method of completing the square, where you complete the square, or if you look at Cardano's solution and so on, what happens for cubic equations, okay? So here you get the same thing, what happens to the quadratic form, you get the invariance delta and even a. A bar is actually a here, okay? So, and you get the solution coming up there. What happens for the cubic? Oh, sorry. What happens for the cubic equation? Again, these are the binomial coefficients for convenience. And if you do that linear transformation xy equals to x minus alpha, you find that this equation maps to itself, right? But you can actually annul this quadratic part of that equation, and you get this equation here. And you find that these are the discriminant, this is the discriminant, invariant, and that is invariant. You get the two invariants, okay? And in Ferrari's solution, basically, you should actually, normally the threes are not there, these threes are not there, but you get that the solution of this equation here, the solution of this corresponds to what Ferraro and Cardano did during the Renaissance time. Okay, so basically you get, apart from A delta, you also get another invariant coming out here, and the solutions are given.
H negative.
Yeah, the H is negative. There's a minus sign here, but the H is.
So the constant. Why not plus?
You can put it as plus, but then you make this as minus. So then this is keeping in mind what happens if you go higher to quartic equations and cubic equations. I think people know the result. Those of you doing pure maths, that Galois theory says that if you any equation below the cubic equation, which the solution can be written in terms of radicals and the basic signs, right? You can write it in terms of here. You can write in terms of the solution in terms of cuboids and so on. However, the solution of this equation here, right? Although everybody thinks it's straightforward, right? Because you know the formula. What is the best way of actually obtaining the solution of this here in a systematic way? And that hasn't been done. Okay? We know that the permutation of roots, the permutation of the roots have certain invariant properties, the group properties, meaning that this equation can be solved, right? But the simplest way in which this equation can be solved is not known. There are two ways in which this has been done in literature, right? You can go look at the works of Ferrari, Cardano, who displayed Ferrari's solution, and that's what you find in books, right? Or you use the quadratic equation to solve this and so on. And there's another one that many people don't know, and this is called Schoenhausen's transformation of 1683. Right? Now, those of you honest students, or those of your professors, go look at this paper. It's an interesting paper. It's about 4 pages in there. Okay, and how we obtain the solution of the cubic equation in another way compared to what Cardano did. Now the question, open question, can you obtain the solution of this equation in a third way by using symmetries? Okay, now, so we spoke about algebraic invariants, and now, at the same time in 1773, Laplace also considered invariant, but I'll speak about that just now. Differential invariants are also considered by some of the French mathematicians, leading mathematicians in 1879, 1880, at the same time, right? So Laguerre, Mallet, Alphen, and others. This was mainly for scalar linear ODEs. There's a connection between algebraic invariants and linear O-derivative differential. In fact, even the English mathematician Forsyth, there's a book of Forsyth in the library. I think there are 2 books. Right? One is 1924 and one is 1888. There's a paper of his, made seminal contribution in this area. This was mainly for scalar linear ordinary differential equations. Right? Now, this is the second order most general equation. The 2 is for convenience here. If you do just change of the dependent variable of this term, this equation here, if I substitute y equals to y bar upon sigma into this equation, it maps into itself. It becomes itself. However, the coefficients change, a, b, and c change. Okay, right? And what happens as a consequence of doing that, just like what you did for the algebraic equations, for the quadratic equation, you find that this A is an invariant, and lo and behold, what happens here? Notice this delta, which is b squared minus ac, comes up here. But because it's a differential invariant, because I've got a derivative, this term comes in additional. Let's say compare the quadratic because delta comes up here. Now, Forsyth noticed this here, and of course the Laguerre, Mallet, Half, and so on noticed this, but they didn't pursue. Forsyth did this more generally, and if you do this for, oh my goodness, if you do this for this third order ODE, again the 3 is the binomial coefficient for convenience. The invariance of A delta resides even higher. If you don't put the binomial coefficients, what happens? The invariance do not respect it. They don't come up higher. Okay. So here, if you do this linear change of variables, and I substitute y equals this y bar upon sigma into this equation, it maps into exactly the same form, except now everything is barred, and b bar, you're going to get y bar triple dash 3b bar y bar double dash 3c bar y bar dash plus d bar y bar, and b bar, c bar, and d bar will be in terms of sigma and the old coefficients b, c, and d. I put a equals to 1 here. Okay. Here, what you find is that you're going to get your invariance for your second order equation persisting further, and that is the delta. Notice I put a equals to 1. If I go back, if I put a equals to 1 here, this becomes just b dash, and this becomes b dash. Right? I put a equals to 1. So here you get this here, and you get another invariant J. Okay? If you go to the fourth order linear ODE, you find that the same thing persists. The invariance built with the delta and h and what you can call it f and j and so on of your algebraic equation persists here, right? So I'm not too sure how far Forsyth went into this. I don't think he did the general case, so it's no problem. Okay, but I think anybody can do it. It's easy to look into this and see what they is there. So notice there's a correspondence between the algebraic invariance and differential, right? Okay. Now, what's the help of this invariant? If I have a ordinary differential equation of second order linear one here, notice the variable coefficient. If I ask anybody to solve this, and you'll say, but I can't do it. And this kind of stuff occurs in relativity also a lot, right? These kind of equations, right? However, if you look at if you work out the invariant of this equation here, the I, which I gave before, right? And if you work out the invariant here of the simplest equation, you find that I bar is 0. And since the I and I bar have to be the same because they remain the same, right? You can actually construct the sigma to be this here by means of that transformation. And you can reduce this equation to that equation here, like that. Like how you're solving the quadratic equation by nulling, because you know the invariance. You can actually solve here, because you know the invariant, you actually can solve this and reduce this to, although this is a variable coefficient equation, right? A lot of times this passes our eye and we say we can't solve this variable coefficient, right? Except if it's like the Euler-Cauchy equation, like we have x squared here, x something times x times y dash plus constant term y. Then you say it's Euler-Cauchy equation, you can do it. But also the Euler-Cauchy equation has invariant structure in it, and you can map it to simple form. So this is the beauty of invariance, how you use invariance to actually produce an equation, okay, to solve them. Now, if you do the characterization of nth order scalar linear ODEs, the folklore suggests that it should be the same as for linear second order equation. And the answer is not the case. And that only became unraveled in the 1990s. This was because of the works of the French mathematician Krauss, unfortunately, they made a mistake, and again, they thought it was the same, that it was equivalent, the structure is the same as the linear equation. And then, because of that mistake, we found that this isn't the case. What the question?
I was just wondering, in your 2007 paper, when the equation is not linear and can transform it to y or prime, this is not x matrix. Is that true for this?
Yeah.
For the linear equation as well?
Yeah.
This equation is just even the Lagrangian is nice for this. Will give you that.
Yeah. The Lagrangian's got 5 symmetries.
5 symmetries.
Yeah. Well, I'm not going to confuse everybody with that. I'm not going to confuse this lot here. That's why I'm going over slow here. Okay. Are there any questions from you guys? Look, the main idea so far I'm talking about is the invariant structure, the patterns that you see, right, manifest themselves in a more complicated way. If you underpin something, if you try to look at something, even if you look at yourself in a mirror, right, you see the same person, right?
We won't.
The mirror person is not the same as you are, right? The mirror person's got his or her heart on the right hand side, whereas you got your heart on the left hand side, because the left and right inversion. How the number theory probably still comes from. I mean, you don't know the prime sequence, for example, right? Okay. So like that for differential equations, these are things. Okay, I'm going to answer some of the questions that you've been asking. This comes up in a work of Treswa around 1896, that if you've got a second order equation, you can reduce it to the simplest equation possible, which is y double dash equals 0, right? If and only if these quantities here, which is in terms of this f, if you derive it 4 times with respect to y dash, partial derivative, and here partial derivative, and then you do a total derivative here, and this combination, if both of these are 0, right, this equation here reduces to the simplest equation, which is y double dash equals 0, right? Now, how to unpack this a little bit further? Okay, so I mentioned references very badly here. I'm not saying who these people are. You can say me here. I didn't mention the name here, obvious reason. So, in fact, what leaded before this, it preceded what Chess was a student of me, right? What leaded is that if I have an equation of this form here, in fact, if you go back here and I say this vanishes, it means that this f has to be cubic in the first derivative y dash, right? So this is exactly what happened here. So what leaded, we assumed this cubic thing here. He didn't assume it, he actually showed that it has to be cubic by using invertible transformation, but the point I don't want to stress on that. If you assume this here, he showed that if these I'm calling it E3, E2, E1, I'll pull this out of one of the papers. If you look at these coefficients, if it satisfies this system of 4 equations here, where B and E are auxiliary functions, again there are things that are not known about this system. One of the things that are not known for this system here is, if I have this system here, overdetermined system, right? How do I construct the maps that reduce this to the simplest form? I'll mention a bit more about that, how you can actually do that. But I don't know how to do it for this particular thing here. So these are auxiliary variables, B and E. This equation is linearizable if it satisfies the overdetermined system. When will it satisfy the overdetermined system? If you have compatibility conditions being holding. Now what I did, I pulled this out from the other papers. So the E2, E3, E1, and E0 is actually the A, B, C's, and D's, right? So here, if I go back here, right? If I differentiate this with respect to Y, this with respect to X, equated with each other, right? If I differentiate this with respect to Y and this with respect to X and equated with each other, right? Then the equation is compatible, then what you get is exactly these 2 conditions here. And what do you note about these conditions? Stress conditions actually reduced to this here, these 2 conditions, right? What does it mean? If I have an equation of this form, A, B, C, D. Anybody can check this, right? Take an equation, right? Cubic. It has to be cubic, right? If the coefficients A, B, C, and D satisfy these two conditions here, then and then only this equation can be reduced to the simplest equation, y double dash equals 0. Okay? But then the problem comes, how do you construct the maps, right? How do you construct the maps, right? People have been trying to do this. So in other words, I need to look at the transformation, like for example, how do I reduce the quadratic equation to its simplest form? I do a linear transformation in X, right? Now we have got two variables, X and Y. What transformations I need in X and Y to reduce this equation here, this equation here, to the simplest equation in the new X and new Y, right? Simplest form, y double dash equals 0, say capital Y double dash equals 0. What are the transformation? How do I do that? Okay, there are a couple of methods here. In fact, they're about what? They're about 5 methods how to do reduction to simple form. Now, in only one of them, you can actually construct the transformation. And that comes from geometry, from geodesic equations. When I know geodesic equations, I know the geometry, I know the manifold structure, I know whether the space is flat or not flat, and so on. And if I work with the Riemann tensor, which is in terms of, I mean, this is the way out, I'm just saying something now. If you put the Riemann tensor to be 0 for flat space, right? And you project that, if you project the geodesic equation to a third order cubic equation like that, you get precisely these conditions. And not only that, by doing that, you can actually simplify the metric to the flat space metric, right? You know what I'm talking about, right? If you do that, you can actually construct the transformation. Right? There's a paper that I wrote some years ago. It got the content of that particular thing, right? So you can do it by using symmetries of manifolds, okay, geodesic equation. You get exactly this condition here, and you get, of course, many other things coming up as well. Now, another method is a method due to Cartan. Cartan came just after Lie in the 1900s. L.I. Cartan is a French mathematician, and he used finite transformation to reduce one equation to the other, right? So what he did was he associated the geometric structure with the differential equation. When you associate the geometric structure, it enables you to look at the geometry of that equation, and you are able to reduce it to simple form, right? And then what these guys in Grissom and Thompson Ahmed did was, these guys from America, North America, they used the Cartan method, and they arrived at the Lie criteria, basically the two conditions I mentioned earlier on. In fact, not the Lie criteria, the compatibility of the Lie criteria. This was done in sometimes in the 90s, I think. Yet, this is a geometric approach which I mentioned about just now. You can derive Lie's condition. Also, you can construct the transformation. Now, in this particular paper here, which is open, the problem that's open here is that I can use the Cartan method, right? It comes up, I get certain conditions which are similar to this here. In terms of compactly, I can get this function f coming up, right? In the Cartan method for reduction to simple form. However, the transformation is not easy to come up to do the reduction. There's some Riccati type equations coming up. So it's an open problem how to actually construct those transformation in a simple way possible. Now, what happens? It becomes more difficult if you go to. Okay, I'm going to just quickly say here. It becomes more difficult if you go to third order equations, because there are 3 classes for linear forms, right? And that's an open problem that Uh, uh, we we solved two of them already, so that's just recent work with co-workers I have. And we use a kata method, and not only that, we're able to obtain the transformations. Maybe I'll even talk about that sometime, but that's a bit more complicated. Now, let's go back to, like I said, there was a coincidence in 1773. Two things happened. The algebraic invariance came about, right? Then it gave rise to algebra of forms, n-ary forms, and so on, quadratic forms, cubic forms, and so on. And you had the basis theorem of Hilbert coming up. Then, side by side, you had differential equations coming out there, right? Legge, Fazal, and all these people were there, Haufen, and so on, right? Looking at ODEs and the correspondence with the algebraic ones, right? And then at the same time, picking up on what Galois did for algebraic equation, proving that you can't solve a quintic equation in terms of radicals, Lie came about. And he said, I can solve differential equations in terms of so-called solvable groups, right? Solvable groups, like how you have permutations, like, you have the quadratic equation, where x1 plus x2 is minus b upon a, x1 times x2 is c upon a, right? If I permute the roots, that relation remains the same, right? If I permute the root, that relation remains the same. If I leave the roots same, x1 plus x2, the identity, that's identity transformation. So the permutation of the roots leaves the root space the same, right? If you do the cubic equation, you get three relations in terms of the roots. And again, the permutation group, if I permute the solutions, it remains the same, right? However, if you go to quintic equations, you analyze the group for the quintic equations, right? The permutation group. It has a structure which is called non-solvable, right? Meaning that you cannot solve a fifth degree equation in terms of fifth roots, addition, subtraction, multiplication, division. Can't, right? If it's irreducible, you can't solve it. If there's a factor, you can reduce to a quadratic equation and you can solve, right? So, for differential equations, he tried to do something similar, but it happened to be different, right? Just to complete the picture this far, there's a lot here, like I said, right? I mean, no matter how much I talk here, I can talk from now till I die. If I die too quickly, it's not going to be enough. If I die even later, it's not going to be enough. So what I'm saying is, there's a lot of missing links in the story, right? But one of the prominent aspects is the same possible. Okay. One of the prominent things is during 1773, there's a couple of pictures that are coming in place. One in 1773 was the algebraic invariance, birth of that, right? For algebra in Lagrange's work. Algebra forms, Hilbert and so on come up there, and then Fazal, Legge, Hamid, and all of these people come out there, right? And there were some side stories also there. There was Lie residing there, trying to look at what Galois did, right? And trying to prove solvability for differential equations. But that was a different picture, right? And then in 1773, what happened was Laplace noticed something for partial differential equations, right? He noticed something for partial differential equations. And this was only resuscitated in the 1990s when Ibrahimov was here. Ibrahimov, like I was telling Warren, was one of my teachers. He taught me, he taught Joel also, and he didn't teach you, he taught Kamal, right? So you're too young for that, right? So, I mean, he played an important role. He was a mathematician from Russia. He won the USSR State Prize in 1987. So he, because of the pension problems and Paris, what's this changeover of communism to capitalism? Some of the people didn't like the changeover, right? So he came to South Africa and managed to get him a position here by pestering people here, although I was junior. And I managed to get quite a few people positions there, by the way. So not of the same color like me, different colors, right? So what I'm saying is he came, it was a good fortune we had, and I think Prof. Mason was also here at that time. Prof. Mason was in symmetries of space-time and relativity, then continuum mechanics, and it came symmetries of differential equation, fluid mechanics and stuff like that. So Nile inspired a lot of us, and of course before him was Peter Leach, who did a lot for the differential equation, classical mechanics. Prof. Mason knew Prof. Leach quite well. Prof. Leach is in Durban at the moment. So in what Nile pointed out was that in 1773, Laplace actually knew that there were invariants of differential equations. And these were linear equations that you're going to see in your course, in your fourth year course, right? And I point that out. And these invariants are so beautiful that they enable you to actually reduce second order linear equations to first order and actually to solve them. It's really, and the idea behind those so-called, the idea behind this Laplace invariant, I quickly mentioned this, I'm going to stop. Okay, so these are invariants, just like the invariants we had before, right? Notice these are in terms of the coefficients of the equation, A, B, C. They have first derivative here, so they are differential invariants because they have derivative. Algebraic invariants, they have no derivatives, right? Again in 1773, coincidentally, and not for the elliptic equation, for the hyperbolic equation. Again, see, look, some simple errors I'm making there, right? It's for hyperbolic equation, and this is this fundamental memo of 1773. These two quantities here are unaltered under the linear transformation. Notice we've seen this for linear ODEs. Can you see this transformation here? Right? Well, except now you've got a U and U bar, right? If I substitute U bar over sigma into this equation, it remains the same form, right? And what comes up of that is these two equations. Very transparent way. Just like how you saw it for the quadratic equation, right? It comes out in a beautiful way, right? And these invariants are only invariants under this particular transformation. So it gave rise to a lot of studies during that particular time, but that was forgotten until, like I said, in the 1990s, when I brought them off. And I gave a talk on it, I remember in SAMS, and I had some weird questions people were asking me from the numerical people. What do you do with this invariance? You know, why do you need? So like telling yourself, why do you need to look at the mirror? Right? Why do you have to look at the mirror? Okay? Because you want to see yourself. You want to see how beautiful you are, right? Okay. Now, okay, so I'm going to stop here. And look, there are quite a few things, and there's some exciting stuff. I mean, there are some experts here. There are two big experts sitting there, Prof. Kara and Prof. Mocheki, who's head of school. Prof. Kara was also one of the leading people in the country in these things. So there are many things that they are doing and have done, which are really nice, using some of the things. I gave very simple talk here, so they'll be more complicated talks. So, and then Warren is working on some interesting problem on what we call taboo transformations. This is a little bit more general than this particular transformation, where you look at a derivative here, right? Okay, but you do the same things like I'm talking about here, right? And you get some beautiful properties coming out there. And one of the consequences of these Bakelin transformations is a Hopf-Cole transformation. Like you can reduce the Burger's equation to the heat equation and so on. Some beautiful stuff. In fact, you can actually do that using invariants. I uncovered that recently, and somebody else uncovered that in the early 1900s in a different way. So I did the invariant structure, and you can actually reconstruct the what you call the Hopf-Cole transformation, which has a derivative here, which maps the Burger's equation, which, for those of you who don't know what Burger's equation is, a nonlinear equation to the heat equation. Right? Everything can be mapped to the heat equation, right? All you guys in maths or finance, you want to map everything to the heat. Black-Scholes, options pricing, and so on. Okay, so look, I mean, this is just the tip of the iceberg, and I try to present it in a simple way. I hope I didn't say anything wrong, so just point out to me if I did. And then also, there are a lot of ideas about these that permeates and goes beyond. and for nonlinear equations and so on that are untouched and then one can do. And there's stuff in this you can use for in fluid mechanics, in relativity, in like what Warren was doing in black holes and stuff that he was telling me about recently, and how to use these transformations. The thing is, we live in a world that's full of symmetries. And even though we don't see it, symmetry breaks every now and again, right? Like you see a lot of symmetry, you actually don't see it. When you see the wall, you don't see there are a lot of symmetries in the wall, do you? Right? Basically, like if I rotate part of the wall and leave it there, you won't know that I've done that because it's got symmetry. I can translate, rotate any points on the wall in a local way, because you can imagine the wall as a big part of something infinite, right? When you see a lot of symmetry, you don't see it. Like when you go to the lake, what happens, right? You see everything is beautiful, calm, until your little brother, right, or little sister comes and takes a stone, and she throws it to the lake. What happens? What do you see? The symmetry of the lake breaks from all symmetries to just rotation for that while, right? And after stability reaches, it becomes the same, right? Don't you see that? Right? So when you sometimes you may not see symmetry, although there's symmetry there, and sometimes something will be complicated. You just have to go and unravel the symmetry. So that's what these gentlemen have been doing, and they got lots of works on it. I've just given, like I said, a bit of the story. There's much more to it. How this pattern goes on and on for the stuff that people have done. Many people have worked on it, and literature and so on.